Lava lakes. They are an absurdly common feature in TV and movies to add tension to our favorite heroes and are even in many video games. Yet, despite their perception across the general public as being associated with many volcanoes, here is something that lava lakes are not common. In fact, let me ask you, how many square kilometers do you think the combination of all the world's lava lakes at the present cover, given the fact that there are more than 1,300 confirmed or suspected active volcanoes? 1,110 square kilometers? The answer is far smaller, being a mere 0.178 square kilometers or 43.99 acres. In fact, at the present, only 7 of these more than 1,300 volcanoes currently have long-term lava lakes that have persisted without pause for at least the last month. Let's quickly go over them from smallest to largest. Tonga's uninhabited ring-shaped Tofua volcano, Nicaragua's Masaya volcano, Vanuatu's Yasur volcano, Mount Erebus in Antarctica, Mount Michael in the South Sandwich Islands, Nyiragongo in the Democratic Republic of the Congo, and finally, Nia Moragera also in the Democratic Republic of the Congo. Here is a quick size comparison chart. And since viewers asked for it, here is how these lava lakes would compare to the literal smallest lake possible, having an area of 10 acres, and also comparing them to the world's smallest country, Vatican City. Tofua has the smallest lava lake, which could fit nearly 279 times inside of the world's largest currently active lava lake at the Nia Moragera Shield volcano. This larger lava lake is truly massive, having a width of 413 meters or 1,355 feet and encompassing an area of 98,477 square meters or 24.33 acres. And now, here's a quick plot of the lava compositions within each of these 7 lava lakes. They are widely varied, but across them there is something consistent, a low or intermediate silica content. This is crucial as the more silica-rich a lava is, the more viscous it becomes. More viscous lavas build up above vents or even clog said vents, leading to explosive fragmentation and strong ash emissions that prevent the long-term creation of a lava lake. So, in the future, a lava lake is hypothetically unlikely to form at Mount St. Helens, a volcano that largely erupts dacite, but a lava lake could theoretically form during the next eruption at the Craters of the Moon volcanic field in Idaho, since it largely erupts basalt lavas that have a very low gas content. Gas or volatile content in the magma is also important, as lava lakes can only form with low or moderate volatile content, otherwise they get explosively ejected as ash and do not get the chance to form. While Spanish conquistadors once wrongly assumed that a particular lava lake at the Masaya volcano contained molten gold, lava lakes can actually produce distinctive crystals. At Mount Erebus, which has a highly unusual phonolite lava lake, what prevents an otherwise highly viscous lava from solidifying is due to how frequently the material within it cycles. This cycling motion keeps anorthoclase crystals growing that form within it, allowing them to reach abnormally large sizes when they do eventually get ejected in lava bombs. Here are a few of those crystals I was given from Mount Erebus in Antarctica. However, the mere existence of these crystals proves that another location in the world also once contained a lava lake, meaning their existence are technically markers of fossil phonolite lava lakes. This is how we know that the Mount Kenya volcano, when it was still erupting at one point, contained such a phonolite lava lake, since similar crystals are found on part of its edifice. However, a more general method can be used when looking at an extrusive ancient rock formation to help determine if it too might have once contained an active lava lake. What you want to look for in an area with exposed igneous rock units present is columnar jointing, which forms polygons, typically hexagons that look like this. But the existence of these features is not proof in of itself. They need to be in a particular region consistently strongly curving inwards, meaning that the same columnar jointing polygon will be further away horizontally from their origin point the higher they get. One such example of this can be found at California's Devil's Postpile, which is shown here. As a final note, I would like to thank my new YouTube channel member Richard Bergen for supporting my work.